Okay, let's pick up where we left off last time. Uh, we were working on segment 14. I think we got down to slide 40, and we were looking at enthalpy of formation for different compounds. Okay, now this was a point of one of our lab experiments when we did Hess's law. We saw that if you have a reaction and you have the heat or enthalpy of the reaction written in one direction, if you turn the reaction around, you change the sign of the heat. So if a reaction is exothermic in one direction, it's endothermic in the other direction. Now, one of the things that's going to be really, really important, and you sort of need to keep this in mind, whenever you put things together, and especially as we do it in standard state, remember standard state has all of the reactants and all of the products in that mixture all at once. And so whenever you are thinking about a reaction, when you put all of those things together, a spontaneous reaction will happen. Nature do what nature do. It will either go to the right or it'll go to the left, and nature will decide which way it goes, and we're going to try to discover how nature does that. But when you write down a reaction, nature doesn't know what you wrote down. You could just as easily write the reverse reaction, and that might even be a possibility. But you could write that reverse reaction down, but that doesn't mean that's the way the reaction occurs. So keep that in mind, and that'll make things a little bit simpler as we go further. Now, if you've got several steps that can be added together to create an overall reaction, then those added together, some of those steps will be the heat of the reaction. And you can always write any reaction as a sum of reactions. For example, if I take sodium hydroxide and react it with sulfuric acid, certainly is true, that reaction will go to the right by nature. If we wrote the reaction Na2SO4 and water going to sodium hydroxide and sulfuric acid, I mean, that balances, everything would be okay. The only problem is that's not what happens. Okay, so if we put these together, let's look at a way we can cause this reaction to take place. We could take the sodium hydroxide and the sulfuric acid, and we could just break it up into all of the elements that make it up. Sodium, its standard state is solid at room temperature. 1 atmosphere of pressure doesn't matter, but it would be. And so 2 NaOHs would make us 2 sodium atoms. The oxygen would make O2 gaseous oxygen. The hydrogen in the hydroxide would be hydrogen gas. And if you added up all the atoms of the reaction I'm showing you now, the reactants and products all balance. That's correct. That's a decomposition of all the reactants to their elements in standard state. Now, if you look at the reaction of those elements, I could put them back together and make the products. I can make the sodium sulfate and the water. And then if I added these two reactions together, the sodium from the first one, the 2 sodiums would cancel the 2 sodiums in the second one. The 3 oxygens would cancel the 3 oxygens. The 1,8, the S8. The reason why it's written that way is sulfur's standard state, the actual state you find yellow sulfur in, is solid. And there are 8 atoms of sulfur arranged in the shape of a crown, essentially, as a circle. That is the standard state for sulfur, is S8. So if I add these together, I get the sum of these 2 reactions by Hess's law has to equal this reaction here. And now this has a special way of writing that. I can write for any reaction The heat of formation, it's the sum of the heats of formation of all of the products, you see. This is the heats of formation of sodium sulfate and 2 waters from these elements on the left. That has to equal the sum of the heats of formation of the reactants. I subtract those off. Why did I subtract? Because I needed them turned around. This first reaction, 2NaOH to H2SO4, is the negative. It's the opposite of the heat of formation of the reactants. So it's the sum of the heats of formation of products minus the heats of formation of reactants. And we can put them in the tables. Now, just a few little tidbits. When you talk about calories in your food, it's really what we call kilocalories. So a food calorie is a kilocalorie for a scientist. And when you burn stuff in air, you can get a fuel value for something. For example, like you're burning your Cheerios. If you burn that in air, the heat that it would take, that would be given off when you burn 1 gram, would be the fuel value for Cheerios. And you can do that. Now, the neat thing, way to measure heat flow is to do it in a bomb calorimeter. And you can measure the heat that is given off when you burn a certain amount of the compound in a container whose volume can't change. And this is what they do to give you the calories that's in your Cheerios. They put the Cheerios in the bomb calorimeter, and they put a known weight of them, say 1 gram, and then they burn it in the bomb calorimeter with an excess of oxygen and see how much heat is given off. And that heat per gram then, it's then put on the side of your Cheerio package, depending on how many grams a serving is. So if the serving is supposed to be 20 grams, then they would take 20 times that value, and that would be the heat or the energy of that in calories they put on the side of your Cheerios box. Now, when you metabolize a gram of food, you get a little bit less than the fuel value. So that's a good thing. So whenever you read the number of calories in your candy bar, you're going to get a lot of calories, but it's probably going to be a little bit less than what they list as the calories on the side of the package, but not enough less to worry about, so not a big deal. Okay, let's look at some problems now. Here's a reaction with SO2. It will burn in oxygen to make SO3. Sometimes it's a little hard to get the reaction going, but you can. If you do, it would give off negative. It gives off 196 kilojoules. If you take sulfur as solid sulfur and burn it in oxygen, you can make SO3 that direction. Now what we're going to do is combine those to get the heat of a different reaction. So this goes to the point that you don't have to measure every possible reaction. You only have to measure a few of them. And once you measure one and record what its energy is, like for example, that first one, it's minus 196 kilojoules, I can put that in the back of the book and keep it if I wanted to. And I could do the second one and do the same thing. And then instead of measuring sulfur and oxygen to make SO2, which is not one of the 2 reactions, I can use those 2 to calculate it. It's a fairly simple thing. Now, but I want to show you a strategy. You know, it makes problems a lot easier if you learn an approach. Rather than trying to memorize a pattern for a particular example, if you learn the approach, then if I change the example, it still looks like the same problem to you. So here's what we would do. We want to start with what we're going to call a working equation. And we want to choose the given equation with some species that's found in the target when you want. So I'm looking at this and I'm saying that, okay, um, this is my target equation, sulfur and O2 to make SO2. The most complex thing in it is the SO2 on the right. So what I'm going to do is I'm going to write that reaction as my target and add, I'm going to take this first equation, see, is the SO2. My target has the SO2 in the product. So what I want to do is use this first equation, but have the same coefficient that the given equation had, and the given equation set up so that it would be opposite, cancel out, of the target equation. So I want to be sure to put this on this side of the equation. Okay, and now, so I want to turn this reaction around like this so that it is now showing the SO2 the way I want it to be in the target. But now I want one SO2 in the target product instead of two. So I want to divide through by 2. If I turned it around, it was minus 196 originally. I turned it around, so now it's plus 196. And I want to adjust the coefficients so that it has the same coefficient that my target has. So I need to divide through by 2. So if I divide through by 2, I need to divide the heat by 2. And if I do that, I would get plus 98. Now from here on out, we want to get rid of something that's in this equation that's not in the target equation. Well, SO3 is not in that target equation. And so I'm going to eliminate the SO3, and I'm going to do that using the second equation that was given. And I want to set it up in a way that the SO3 will cancel. So this now is my working equation. So my working equation to start out with was one of the original equations that had the most complex product, complex part of my target equation in the correct side with the correct coefficient. Once I've done that, that gave me a new working equation. From here on out, we're getting rid of things in that working equation. So I need to add to that then. There's the SO3, and it's at plus 96, 98 kilojoules from there. I want to add to that my second equation, the 2 SO3 plus 3 O2s go to 2 SO3s. But again, I can't cancel them unless they have the same coefficient. So I want to divide this coefficient also by 2. It's heat. I didn't change. It's in the same direction it was, minus 790 kilojoules. But I do need to divide everything through by 2. And when I do that, dividing the minus 790 by 2, I get minus 395. Now I want to take this equation and add it to my original equation, my working equation, and get a new working equation. So now my SO3s is canceled. One of the O2s cancel, 1/2 O2 cancel from each side, leaving 1 O2 on the left side. And then the SO2 is the only thing that's left. Now, this becomes my new working equation. But now, every time once you get a working equation, you go back to see, is this the same as the target? If it is, you're done. And I added these 2 equations to get this. So I repeat that step always. And if I had more given equations, I could put more of them together. And generally, you only use one of the equations given one time. And you keep doing that until your working equation is equal to the target equation. When you're done, you're done. Okay. So in this case, we're done. Now here's a checkpoint on that, and it's a little more complex equation, but let's think about it again. Here are some given equations. I have 3. And here is the equation I'm trying to calculate. Now, I need to pick something to start with a working equation. And I'm going to look at this target, and I'm going to pick the most complex looking equation present. It could be either one of these two. Certainly I wouldn't do hydrogen, but C2H6 is a little more complex. I might look at that. And I want to find the equation that has this one in it. Okay, this first working equation then, I'm going to get by, see, this is the C2H6 needs to be on the reactant side. It is in the given equation, but its coefficient given is 1. So I want to divide through by 2. Divide 2 by 1, I get 1. Divide 7 by 2, I get 7 halves. Divide 4 by 2, I get 2. Divide 6 by 2, I get 3. Divide by minus 3119.4, I get minus 1559.7. So now this becomes my working equation that does have my C2H6 in the reactant side with the coefficient that I want. That becomes my working equation. Now, what do we do with the working equation? We want to get rid of something out of the given equations that would cancel out something that's in that working equation. And we're going to leave the C2H6 alone. We'll never touch that again because it's right. But now if I reverse the second equation to eliminate the CO2, well, okay, my working equation has 2 CO2s in it. If I turn this one around, it would have 2 CO2s. So 2 CO2s and 2 waters would go to C2H4 and 3 O2s. But I turned it around. It was minus 1410.9. Now it'll be plus 1410.9. Now I'm ready to combine them, the two together, to produce this new working equation. So I add this equation to this one, and it's going to come out to be minus 148.8 kilojoules. And it's still not done. I've got to get rid of something that's in this equation in order to complete it. And I don't want any O2 in my balanced equation. So I want to get rid of the O2, and I'm going to do that by taking the third equation and add that to this one to give me my, so if I reverse the third equation, divide by 2, then I've got this equation. Now add those, that's going to be good when I put those together. The working equation now is this number plus this number, and so we got it. And our heat of the reaction we obtained because it was now the working equation and the target equation were the same. Okay. Now this is a checkpoint on it. It's sort of similar to the other one. I'm not going to work it out for you, but you can look at this and you see what I want is the heat of formation for this reaction here, strontium carbonate. And remember I told you when we talked about heats of formation, it's generally impossible to actually do that reaction. You know, if I mix strontium with carbon, I could make strontium carbide. If I mix strontium with oxygen, I definitely would make strontium oxide. I wouldn't make a speck of strontium carbonate. But that doesn't keep us from being able to calculate its value using these three equations that are known, and these are the heats that absorb from them. So just to get you started, I'm going to look at this thing right here. It's got strontium carbonate with a coefficient of 1 on the product side. I want to find strontium carbonate in these three reactions. One of them has strontium carbonate in it, and I want it on the product side. to produce my first working equation. And from then on, you add these other equations in the form that will eliminate something that's in that first working equation. And I think it's probably going to be strontium oxide is something you're going to want to eliminate, okay? All right. Okay, here's another use of the heat of formation of products and reactants. Here's an oxidation reaction with ammonia to make NO and H2O. I chose this because it's kind of an interesting reaction. You really wouldn't want to do it, but if you were to take ammonia and concentrated ammonia is just 15 molar ammonia, but it produces a very potent gas. It really stinks. It's crazy. But if you put some concentrated ammonia in a beaker, and then you take a copper penny before they put them together in that sandwich. You know, they used to be made out of real copper. So if you took that and you heated a real copper penny and you suspend that over that ammonia, it catalyzes this reaction. It makes NO and water and gives off a lot of heat. So much heat that the ammonia of the copper penny will stay glowing red hot as long as there's any ammonia in that beaker. The reason why I said don't do it is because it makes this oxide that is toxic. If you were going to do it, we'd do it in the lab. If we were having lab, I could show you that reaction, but we're not. Okay, but anyhow, it's a good reaction. And the way we get the heat of reaction, it's the heat of formation of the products minus the heat of formation of the reactants. So here's the heat of formation of ammonia. That's a reactant. It's negative 46.11 kilojoules. The heat of formation of NO is plus 90.25 kilojoules. Heat of formation of water as a gas is minus 241.82. Now, you do need to be very, very careful to check the subscripts, the phase of the substance, because you will find water in your table of heats of formation as solid, liquid, or gas. And you have to make sure you're using the phase that's in the problem and picking out which of those three numbers to use in the reaction. Okay, so we're going to take 6 times the heat of formation of gaseous water, plus 4 times the heat of formation of nitric oxide or nitrogen monoxide, both names are appropriate, and subtract off 3 times the heat of formation of ammonia. I can plug in the numbers. The heat of formation of water is minus 241, right there's the sign, minus 241.82, and 4 times the heat of formation of NO is plus 90, minus the heat of formation of ammonia. So that's minus, there's 3 of them, 3 times the ammonia value is minus 46.11. Now, be really, really careful. If you're going to do this, do it exactly the way it shows and use the minus sign on your calculator. What I'm going to do looking at this is I'm going to say, okay, this first term is negative. Plus 6 times minus this gives me a negative number here. This second number, plus times a plus, gives me a positive number. So the first number is negative, the second number is positive. This number is minus 3 times minus 46, minus times minus is plus. So the second one and the first one are both positive. The second and third are both positive. The first one is negative. The way I'm going to do it in the calculator is I'm going to write 4 times 90.25 plus 3 times 46.11 minus 6 times 241.82. I always double check that to be sure I get my signs right. It's awful easy to make a mistake. So be very, very careful when you do the math on a problem like this. Okay, here's your problem on the same thing. It's a similar type reaction involving some of the same things. Um, and remember, it's the heat of formation of products. 2 times this one, plus 2 times this one, minus 2 times this one. Hydrogen's not included because it's standard state. H2 gaseous at 1 atmosphere pressure, 298 degrees, is 0. That's the standard state for hydrogen. And 5 times 0 is still 0. So we don't include the hydrogen as a heat of formation because that's part of the standard state. Okay. All right, now let's do some problems involving reaction and heat flow. We worked them just exactly like we've worked all of our problems. How much heat is involved when 3 moles of benzene react with 12 moles of oxygen? This reaction, 2C6H6, that's the formula for benzene, plus 15 O2s goes to 12 CO2s and 6 H2Os. I think that's one of the reactions we did in balancing equations way back in Gen Chem 1. But the heat of that reaction is given. It's minus 4394 kilojoules for the reaction the way it's written. In other words, with 2 moles of methane reacting, you get minus 4394. It gives off 4394 kilojoules. If I had 1 mole, it would give off half as much. If I had 4 moles, it would give off twice as much, etc. 2 times 2 would be 4. Okay, now, how much heat is involved when 3 moles of benzene? So I write over the benzene 3 moles. That's what's given in the problem. I look at the balanced equation, it's showing 2 moles. So I write under the benzene 2 moles. This is what's shown now in the balanced equation. The problem has 3 moles, the equation is showing 2 moles. If I look at the 12 moles of oxygen, the problem has 12 moles in it. The equation has 15. So I write 15 moles under the oxygen. So the problem says 12 moles. The balanced equation shows 15. So this now is a limiting reagent problem. You have 3 moles of benzene and 2 moles in the problem. Its really balancing factor is 1.5. If I have 12 moles given in the problem for oxygen and the equation showing 15, 12 divided by 15 is 0.8. So oxygen is going to be the limiting reagent, and all I have to do to get the answer is multiply the limiting reagent rebalancing factor, 0.8, times the quantity shown in the balanced equation. Quantity shown in the balanced equation was minus 4394 kilojoules. Multiply that out, that gives us the answer. Now, let's look in a little more detail. I've told you in the discussion that the internal energy of a system is made up really of 2 parts. It's the energy between the atoms, the intramolecular forces, the forces in the atoms, the bond strength in all of the atoms. Plus it includes the way the molecules interact with each other. So if we had ideal gases, we'd have no interaction energy between them. So it would only be due to the energy stored in the chemical bonds. So chemical potential energy is stored in the chemical bonds that make up the molecule. Now, the way you make reactions take place, is you take all of the atoms that are bonded together in the reactants and break them apart into atoms and see how much energy that would take. And then you take all of those atoms and recombine them in a different way, the way they are in the products, and create new bonds for the products. Now, one of those sides, one of those reactions might be larger than the other one. And if it takes more energy to break the bonds and you get back in forming them, the reaction is going to be endothermic. But if the product bonds are more energetic and you get more energy back in forming the products than you had in the reactants, then the reaction will be exothermic. So here are some typical bond energies. Now, just so you might know where it comes from, there's a device we talked about, gosh, I believe that was back in Gen Chem 1 too. It's called a mass spectrometer. And what it does is you inject a sample into a mass spectrometer, and what it will do is it's so energetic in there that it will ionize the molecule, knock electrons out of it, and eventually it'll break up bonds within the molecule into little pieces, little fragment bonds. And you can tell how much energy you put into that ionizing chamber and then see at what energy a particular bond fragment shows up on the mass spectrometer. For example, if you put lots of different compounds, let's imagine it's water, but it might not be. Water has an OH bond and has a molecular weight of 17. You would need to put in 464 kilojoules per mole before you start seeing the mass 17 peak show up in the mass spectrometer. So we use a mass spectrometer to measure a particular kind of bond that shows up in molecules. And here's just a few of them. And there are lots of different molecules that have OH bonds. All alcohols do, all organic compounds do. A lot of compounds have OH bonds in it. And what they do is they take all those different kinds of molecules with OH bonds, they get the energy of that mass 17 OH peak in all those different things and then average them together. And this is the number 464 that we are going to use as the bond dissociation energy, the energy you would have to break up to break H atom away from an oxygen atom in an OH bond fragment, 464. And for oxygen to oxygen single bond, peroxides have that, and it's easy to break. It only takes 142 kilojoules per mole to do that. Oxygen in air is diatomic, and it has a double bond between the molecules. That's 502. So that double bond is much, much stronger than the corresponding single bond would be. And look at the bottom one on the list is nitrogen. Nitrogen in air has a triple bond in it, and it takes 945 kilojoules per mole to break the bond between oxygen and nitrogen molecules in air. It's one of the strongest chemical bonds known. And it's kind of interesting to me, it becomes a dilutant for the atmosphere. It's good. Oxygen is so reactive, we have to have something to dilute it with. And there's really not much in the way of choices of gases that we could put into the atmosphere with oxygen and use that to dilute oxygen so we could breathe and not poison us by putting something else in there. For example, chlorine is a gas at room temperature, but we certainly wouldn't want to mix that with air to make the dilution. But nitrogen is perfect. It's so good that we can breathe the oxygen, we can burn things in air, you can burn your fuel in air and do all that kind of stuff. And generally, the nitrogen in air just comes along for the ride. Now, high temperature, you can break those up, and when that happens in your car engine nowadays, it does make NO and NO2 and lots of different gases inside the combustion chamber at that high temperature. But when that burned fuel is ejected back out through the muffler system, you have catalysts in the muffler system that convert the nitrogen oxides back to nitrogen into gas. And so you don't put those out in the atmosphere anymore. So this really solves a lot of problems with pollution. But what also happens though is when the nitrogen and oxygen react together in a lightning bolt, then the nitrogen oxides are formed. The nitrogen oxides turn out to be soluble in water, and they dissolve in the water. And when you have a lightning storm and all this going on, you often have rain. The rain washes those nitrogen oxides down and converts them to nitrates. The nitrates then are food for our plants. So it produces plant food. In fact, we get more nitrates in the soil from lightning and natural sources than we put on with fertilizer. But it produces, so putting nitrogen in the atmosphere to dilute the oxygen for us to breathe produces food for the plants, and the plants grow and become vigorous with the nitrates they receive, producing more and more oxygen for us to breathe. So the cycle is complete. So it's a very perfect combination for all of our life on Earth to have an atmosphere of oxygen diluted with nitrogen. Perfect. Okay, now let's use the Hess's law and bond energies to estimate the enthalpy of some reaction. So what we're going to do is we're going to take the reactions, we're going to break all of those bonds, and we're going to form gaseous atoms. Then we're going to recombine the gaseous atoms to form new product bonds. So if we go across this way, we might measure the enthalpy of the reaction. If we go around this way, we can calculate it, and without having to measure it. Okay, here's an example. And to do these kinds of reactions, you have to write out the Lewis dot structure for the molecules so you can see the atoms that are bonded together. And we've gone over that already in the course, so you might want to review that to see if you can write out these kind of valence bond models for different kinds of molecules. Here's CH4 and chlorine. And CH4 has 4 carbon to hydrogen single bonds. Chlorine has a chlorine to chlorine single bond. I've not shown lone pairs. There would be 3 pairs of lone pairs of electrons around each chlorine if we had all of them shown. But if I carry out the reaction, and we do this, it's a process industrial, they do chlorination. So they can take chlorine and you can chlorinate this hydrocarbon to make the methyl chloride, or chloromethane is a better name for it, and HCl gas. You know that's hydrochloric acid. So this is the product of the reaction. We're going to form these products from this set of reactants. Now, the bonds that we're breaking, we have 1, 2, 3, 4 CH bonds. Each one of them is 414 kilojoules per mole times 4 moles. So that's going to be the energy involved in breaking these 4 bonds. We're going to also break the Cl to Cl single bond. On the table, it was 243 kilojoules to make that happen. Now let's look at the bonds we're going to form on the other side. We're going to have 1, 2, 3 hydrogen to carbon single bonds. And they were 414, so we got 3 of them. Then we've got an HCl bond, and we've got 1 of them. From the table, that bond was 431 kilojoules. And we have to break the carbon to chlorine single bond here. That bond is going to be formed, I'm sorry. So now, if we add all of these up, this is the amount of energy in broken bonds. That's a positive number. It takes energy to break a bond. And this sum is 2004 kilojoules, but that's going to be energy released when those bonds are formed. So it's that heat is negative. Well, before I do the next click, I'll tell you something that you might hear said, for example, in your biology classes. What they say is actually true, but the implication is totally wrong. What they're apt to say is that you have high energy bonds in your food molecules. And those high energy bonds, when they're metabolized, that food becomes carbon dioxide and water. And the products, carbon dioxide and water, are lower energy bonds. They are negative. That's why they're lower. They're lower energy and negative numbers. Okay, so what they say is that the bonds in your food, it's like you just, they're like little capsules. You just break open the capsule for the bond and the energy comes out. That's just absolutely wrong. It's the energy comes out because you change the bonds from the high energy bonds in the food molecules to the low energy bonds in the product, carbon dioxide and water. That's why it happens. And so what they say is true. You go from high energy bonds to low energy bonds, but breaking bonds does not release energy. Forming bonds releases energy. Breaking bonds absorb energy. So the energy of this reaction is negative 105 kilojoules when you add these two numbers together. Now that means it does give off energy. It's exothermic. And this reaction would be minus 105 kilojoules for the reaction way it's written. Now, if you do heats of formation of products minus heats of formation of reactants, the actual value is minus 119 kilojoules. I wanted deliberately to show you this so that you can see that when we get energies by bond breaking and bond formation, these bond energies are averages of all the possible kinds of hydrogen to hydrogen to carbon single bonds, no matter what else is attached to them. Now, if I looked at the methane example, for example, in the mass spectrometer, you could measure the appearance potential when you broke this carbon to hydrogen bond. You could find out what energy it took to break off that one hydrogen away from the CH4 and leave CH3. The CH3 would reorganize itself. It would become a trigonal planar molecule, and it would reorganize itself to the point where the CH bond energy to break the second one off of methane, the first one off the methyl radical, is different. And then the third one would still be different. And the fourth one would still be different. This 414 is the average not only of all four of those types of bond breaking in methane, it's the average of propane and butane and ethane and all of the other carbon to hydrogen molecules. So these numbers are just estimates for us. It allows us sometimes to calculate reaction energies for which we don't have the heats of formation of products and reactants. There might be something that's not been measured yet, but we can still estimate what the heat of formation and the heat of the reaction would be using bond formation and bond decomposition. Okay, but it's reasonably good. It's not perfect though. Okay, look what's coming up. This is it, folks. We've covered everything that I always planned for Gen Chem 1, and I really do hope this for you. I hope your dreams and plans for your future do come true, and may God richly bless you in everything that you do for all the rest of your life. Okay, let's stop the screen share now, and I'm going to